Hello, Pathway people. Mr. Klein here. I would like to explain to you how to do problem number 1 on your problem set. You'll see that it's in a spreadsheet. However, you are going to do the work on a separate sheet of paper. The spreadsheet is just to provide you with data and a tool to help you compute things quickly. This problem is about our buddy John Wayne and his 1956 film, The Conqueror. If you've read the setup already, you notice that it seems like an unusual number of people that worked on the set died of cancer, and that could be explained by some nuclear tests that took place in the area shortly before the filming of The Conqueror. We also know that in the general population, 18.5% of people will die of cancer. So your null hypothesis, once again, write this on paper, is that the proportion of people that worked on the film is normal. It's reasonable to assume that it's 18.5%. And your alternative hypothesis is that it's abnormal. It's unusually high. It is greater than 18.5%. Remember that P represents the population's proportion. So I'm going to put in that P is 0.185 here. And I am also going to figure out, I need the number of people that were in the cast or on set. And then I need the number of them that died of cancer. Okay. So I guess it's not the number of people that, no, it is, it's dying. All right. So I think the easiest way to do that is this. If you highlight subject and the cancer rows, really you could probably just highlight the cancer row and you'd be fine. Then you can go up here, data, pivot table, existing sheet, pick a spot somewhere over here. Rows, cancer. So you should see yes and no. And then for values, also choose cancer. And what you'll see is it's going to tell you there are 220 people and 46 of them died of cancer. So my X is 46. My N is 220 people. So the number of successes divided by the sample size. My P hat will be the number of successes divided by the sample size. So our P hat is about 21%, which is higher than the population proportion. Okay. We talked today about how you need normality in order to run one of these tests because you use the normal curve when you are calculating your p-value. So let's check the normal conditions. First, n times p has to be at least 10. So I'm going to say n is 220 times p is 0.185. That gives me a number that is bigger than 10. And then n is 220 multiplied by 1 minus p, also bigger than 10. So these are both bigger than 10, which allows me to conclude that we have a normal distribution. Okay. Moving forward, standard deviation. The standard deviation is, here's our formula sheet. If you don't remember, you can just click on that. But it is equal to the square root of population proportion times 1 minus the population proportion divided by the sample size. So our standard deviation is about 2.6%, and our test statistic is going to be p hat minus p divided by the standard deviation. So it'll look like that. Okay, so our test statistic is z is equal to 0.92. I want to counsel you that a lot of us were making this mistake, not putting parentheses in during the last unit. Notice how you get a totally different number if you do that. Okay, so let's not forget our parentheses. And then our p-value is going to be a norm.s.dist. And that's of the test statistic. Now, if I hit enter right now, it's going to give me the left tail. It's going to give me the proportion of the curve that is below 0.92, which is going to be a pretty big number. I want the proportion above because, as you can see right here, my alternative hypothesis is greater than. So recall that for the norm.s.dist, you need to do a 1 minus. So there's our p-value. It's 17.87%. So we failed to reject the null hypothesis. There is insufficient evidence that the proportion of people that died of cancer on this set is unusually high. Klein out. If I can, how do I get out of here?